Okay, in this lesson we are going to look at functions and their different properties. Okay, so for a quick review on this, we are talking about where we might have an x or a y intercept, and that's going to be where the x or y, where the graph crosses the x or y axis. Now on the next part, an x-intercept, that's going to occur where y equals 0, and a y-intercept occurs where x equals 0. And so a function can have 0 plus x-intercepts, but only at most one y-intercept. So for these first few examples, we are just looking at our x and y intercepts. To start with our x-intercept, notice we have an intercept there at 4, 0. Our y-intercept is going to be up here at 0, 2. For our next example, notice again we have an x-intercept. We actually have a couple of them here. Notice you've got an x-intercept here, 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 and here. So you have a total of 4, and it looks like those are going to be -1, 0. You're going to have at 1, 0, 2, 0, and finally at 3, 0. And then your y-intercept, again, we can only have at most 1, and that's going to be at 0, 6. Our next example, it looks like we have x-intercepts at -4, 0, and also at 2, 0. And our y-intercept looks like we've got 1 down here, so that would be at 0, -2. And then continuing on with these, again, we are just picking out those intercepts, looking at our graph. On number 4, you should have no x-intercepts, and then your y-intercept, we would have 1, that is at 0, 5. Number 5, you should have intercepts at 3, 0, and at 7, 0, and then the y-intercept at 0, -6. And finally, for number 6, looking at this, this one is a strange little function. This one does not have any x or y intercepts. This is none, and down here is none. This function here looks like it might be our reciprocal graph f of x equals 1 over x. That's kind of what that one looks like. Okay, the next part, we do have some vocabulary here, and for this one, it is asking us to define our zeros of a function, and the zeros would be the point or points at which the function intercepts the x-axis, and that is always talking about the x-axis. Very important there. And so to find the zeros, you're going to set f of x equal to 0, and you solve for x. To find the y-intercept, you are going to find f at 0, or that's the same thing as saying that you are going to let x equal 0. Same idea there. Okay, so now we have some good review problems for algebra, and we are asked to find the x and y intercepts of each function algebraically. So to do that, to find our zeros again, this is going to be where we let f of x be 0. So we're going to start off by reminding ourselves that f of x needs to be 0. So I'm going to have 0 equals the negative absolute value of x minus 5, and then we have plus 3. And we are going to try to isolate that absolute value on one side. So we have -3 equals negative absolute value of x minus 5. We can go ahead and cancel those negatives. And so we set this up into two cases. The first case, we just have x equals x minus 5. And then our second case is where we change our sign. -3 equals x minus 5. And now we need to solve those. So If we add 5 over, we have 8 equals x. And then on this other side, we're going to have 2 equals x. So we've found our two zeros, but now we also need to go back and find our y-intercept. The y-intercept is usually pretty easy to find. So I'm just going to put a line through here. The y-intercept, this is where we let x equals 0, or we say we're finding f at 0. That's a better notation. So f at 0 equals negative absolute value 0 minus 5 plus 3. So f at 0 equals negative absolute value of negative 5 plus 3. So we do get a positive 5 in here, but that's going to make the negative on the outside is going to make it negative. And so we see that f at 0 is negative 2. All right, so we found all of our points there. Let's go ahead and fill in down here. It said our zeros. And remember, here you've got a couple of ways you can write it. One way is you can write it in a solution set. That's going to be your braces. And you just list your two numbers. So we've found 2 and 8. It's okay to do that. And then our y-intercept, we can list that as a point if you want to, and that's going to be the point 0, 2. Now, up top, if you want to list those zeros as points, it would have been 2, 0, and then 8, 0. I don't mind which notation you choose. Okay, so now let's move on to our next problem. And again, we are finding the zeros. So to start off with, again, we need to let f of x equals 0. So I have 0 equals 2x squared minus 7x minus 4. And so we need to factor this. And again, whether you do trial and error or if you go through a slide and divide, I really don't care. Just be efficient with it. And this looks like you're going to have an x minus 4 and a 2x plus 1. Now I'm going to set each part equal to 0 and solve. So we're going to have 2x plus 1 equals 0. So that's going to give me x is negative 1/2. And then over here, x minus 4 equals 0, so x is 4. So again, we found our zeros. If we put this in a solution set, negative 1/2 and 4. Now let's go find our y-intercept. So here we're going to find f at 0. And so when I plug in 0, I'm going to have 2 times 0 squared minus 7 times 0 minus 4. So we see that f at 0 is negative 4. So our y-intercept is 0, negative 4. Right, continuing on, again, we've got several different problems here. So again, starting off to find our zeros, that means that we're going to let f of x equals 0. And when we do that, we have 0 equals x to the 4th minus 5x squared plus 4. And again, we are back to doing some factoring. It looks like we're going to have x squared minus 1 times x squared minus 4. And then that's going to factor again. So this was the difference of two squares. And then over here, again, notice we have 4 zeros here. That's crazy. Okay, and so setting each one of those equal to 0, notice that we get x to be 1, or x can be negative 1, or 2, or negative 2. So our solution set down here would be negative 2, negative 1, 1, and 2. Okay, now we can go ahead and do our y-intercept, and again plugging in 0 for f of x, or f at 0, sorry, I said that backwards. So we're going to get 0 to the 4th minus 5 times 0 squared plus 4, and hopefully that does generate a 4. So our y-intercept is 0, 4. All right, so number 10, This one has a GCF. Our other ones have not had a GCF, so we've not really had to worry about it. But this one's a little bit different. We do start out with saying f of x equals 0. And so we have 0 equals x cubed minus 6x squared minus 7x. And let's take care of that GCF. Each term had an x in it, so I'm going to factor that out. And now this turns into a much nicer thing to factor. So we're going to have x minus 7 times x plus 1. And looking at that, we can pull out our zeros. So it looks like x is going to be equal to 0 or 7 or negative 1. So we have our solution set down here of negative 1, 0, and 7. Now we're going to go through and find our y-intercept. And for our y-intercept, when we plug in 0, in other words, when I find f at 0, notice that 0 cubed minus 6 times 0 squared, and then minus 7 times 0, that's going to generate 0 for us. So our y-intercept is at the origin this time. Okay, so for number 11, more of the same stuff we are solving here. So it looks like, again, we have a GCF. And so we are going to let f of x equals 0. So we're going to have 0 equals 3x cubed plus 13x squared minus 10x. And again, we are going to factor out an x. So we have 3x squared plus 13x and then minus 10. And again, you're welcome to do slide and divide or trial and error, either one. I don't care, just be efficient with it. And I'm going to just go ahead and do trial and error, especially since you have a 3x squared, that's going to be prime. It looks like we're going to have 5 and 2, a positive 5 and a negative 2. And now setting each part equal to 0, it looks like x is going to be 0, 2/3, or negative 5. So here our zeros of our function will be 0, 2/3, and then a negative 5. Okay, and then again, if we notice the pattern here, if we're finding f at 0, well, every term has an x in it. So when we let x be 0, everything is going to cancel out, and that's always true here. So again, if you want to just commit that to memory, by all means do so. You are going to get 0, 0 there. Right, so now for our next problem, we do have that square root function. And so that doesn't change things. We're still going to approach this the same way. First step, f of x is going to be 0. So I have 0 equals the square root of x plus 1, and then minus 2 is on the outside. We do need to isolate the radicals, so I'm going to add that 2 over. We have 2 equals the square root of x plus 1. Here we would square both sides, so we have 4 equals x plus 1. So it looks like we're going to get x to be 3. So here our 0 is going to be 3. And then we're going to find f at 0, and again plugging in a 0 here. So f at 0, we have the square root of 0 plus 1, then minus 2. So that's going to give me 1 minus 2, so I'm going to end up with a negative 1 there. So my y-intercepts would be 0 and negative 1. The next part of this, we are going to be identifying some specific points on a graph. We have an infinite amount, but sometimes it's important for us to really just pinpoint some specific ones. And the first one that we need to talk about is a critical point. And the critical point is going to be where the graph changes its direction or its shape. So notice that it's very important for us to note that if a direction has been changed, that is a critical point. Now when we look at extrema are points where the graph changes a direction the function has a minimum or maximum value. A lot of times you will hear that referred to as a relative or absolute point. And then a point of inflection is where the graph changes its shape. But here's where it's important. It changes shape, but it does not change direction. Very, very important there. And this is a wonderful example of a point of inflection. So do keep in mind, you are changing the shape. We're really changing what's called concavity. We're changing from concave up there to concave down. And that's the shape change that this is referring to. Okay, so some more vocabulary. The next part says that if we have a point with the greatest value compared to the points around it, then this is going to be called a relative maximum. Important for y'all to know these because you will be asked to identify them from a graph. And the point where the greatest value over the entire domain of the function, everywhere, then this is going to be an absolute maximum. So notice the difference in the two. This is the greatest value compared to the points just around it, whereas the next one, the absolute maximum, is over the entire domain. The next one, a point with the least value compared to the points around it, that is a relative min. And then a point with the least over the entire domain is going to be an absolute min. And your examples over here, those are giving you some wonderful examples graphically of what to expect when asked to find those. Okay, so our next example, they want us to give the coordinates and classify the extremas for the graph. Now, we're not going to get the graphing calculators just yet. We will be getting those, but right now, we don't need them. We're not going to focus so much. We're just going to approximate. So looking at the first one, whenever we're asked to classify the relative extrema, this is going to be the relative extrema, the vertex. And notice if you count off the coordinates for that, you have 4, -5, and that's going to be an absolute minimum because we know that that is the lowest point over the entire domain. Over the domain. Very, very important. Okay, and then for our next problem, and we're just going to guesstimate here. It's not exact, so it's okay to do some rounding and some good estimations here. So reading this from left to right, this point way up here looks like that is where the greatest value over the entire domain will occur. And that point there, it looks like we've got a negative, maybe 1.5. And then the y value, maybe about a positive 3 or so. So, and to classify that one is going to be your absolute max because that is where the highest value is. Now we do have a couple others, notice here and here, and those we can call those maybe relative mins and relative maxes because they're just the lowest and highest point considering all the other points around it. So let's see, one of those, it looks like, goodness, it's over just a little, I don't know, let's go at 0.2, comma, -4-ish. And so that one is going to be an relative min because, again, it's just the lowest point around it, but not over the entire domain. And then for our next one, looks like right in this area here, so maybe a 1.2, comma, -2.5-ish, and that's going to be a relative max. And it's okay to have a relative max along with absolute. Absolute is over the entire domain. That is the highest value. Whereas right here, if we talked about just a small interval around it, that is a relative max, or it's the maximum value in that small interval. Okay, and more of the same for these. It looks like at -3, 5, maybe around in here, that at -3, 5, -5, that we have a relative min. And then way up here looks like we might have a relative max. And the coordinates there, gosh, that's a little bitty over. So maybe a -0.3, 0.2, something like that. And then that goes all the way up to about 4.5. And so that is a relative max. And again, that's not the highest or lowest point over the entire domain because we have these arrows implying that our graph does continue. Okay, so again, let's start way over here. We have that point there, which is not the largest point over the domain. So I know that's going to be a relative maximum. And it looks like maybe -1.2, maybe 1.3, a little bit past 1. And then all the way up to about 6. And we're going to call that a relative max. And then let's see, right here, notice that we do have an important point here, but notice we did not change directions. We just changed our shape. We changed that concavity right there. So that's going to be a point of inflection. We're going to call that POI because we don't want to write all that out. And that is at 0.3. And then we have another point here, and that one looks like it's going to be a relative min. And that point looks like it's going to be at a little bit past 3. We'll call it 3.1, or 1.3, sorry, going backwards. And then what would be the y value there? Looks like, let's call it 0. It looks like it's pretty close there. And that's going to be a relative min. And the next important characteristic that we will talk about will be increasing, decreasing, and constant intervals. And again, keep in mind that when we look at this, we are moving left to right. So when we trace from left to right, then let's look at what happens if we're trying to identify an increasing interval. Then an increasing interval from left to right would be in this area here. So we would write that in interval notation. It would be from -infinity up to -1. And we're going to leave those open for right now. We could go through the discussion of whether it's open or closed. And if you close it, I will not mark it wrong. But really, it's not going to matter one way or the other here. Now, if we talk about our constant value, then that's going to be through here. So that's going to be from -1 all the way over to 4. And then when we look at our decreasing portion, and again from left to right, notice our graph is decreasing there. And so we would say that we are decreasing from 4 to infinity. So again, y'all talked about this quite a bit last year. Here's another good review of it. Okay, so here we need to pinpoint the intervals where our function is increasing and decreasing. So looking at these first ones, and again, all of these, it looks like they're pretty straightforward. The other ones that we'll see, we'll have to go through and estimate. So reading this from, again, remember you're always reading from left to right, very important. And from left to right, notice that our function is increasing from this point here over. So that's going to be from 3 to infinity. And our function would be decreasing from -infinity to 3. Our next one, intervals of increasing. Notice this function, and this is why it's so important to realize you're reading left to right. Notice this function, as we go left to right, it is definitely not increasing. So this one would be none. And intervals of decreasing, notice it is decreasing everywhere except for at that vertical asymptote. So we're going to say from negative infinity up to -5, and then we're going to pick back up on the other side of 5 to infinity. And then here's a great example. This is an exponential function. And if we look at it from left to right, this little thing is increasing everywhere. So intervals of increasing would be from negative infinity to infinity, and decreasing, that would be none. Okay, on these, we're going to do the same thing. However, we will need to kind of guess to give a rough estimate of where it would be. And so for number 8, if we're talking about increasing intervals, it looks like we should be increasing from here up to here. Now keep in mind you're talking about the x value there. So that x value is going to be somewhere in there. So our increasing intervals is going to be from 0 to maybe, let's say 2.5. Now decreasing, that's from negative infinity up to 0. And then we're going to pick up on the other side of that 2.5, and we're going to go to positive infinity. And it's okay if you put 2.4 or 2.6. Just make sure it looks reasonable for the area. Okay, the next one, increasing, between what two x values would this be increasing? And we're going to say about a negative 1.8. I left off my negative there. Negative 1.8 to 0. And that's going to be our increasing. And then it increases on the other side of 1. So we're going to just say maybe a 1.1 up to infinity. And then our decreasing from negative infinity to negative 1.8. And then from 0 to 1.1. Okay, and then our next problem, again, from negative infinity, our areas of increasing, it's going to be from negative infinity up to maybe about this area right here. So maybe negative 1.1. And then we are also increasing on the other side of 1. We're increasing in that area. So that's going to be from positive 1.1 to infinity. Our decreasing is going to be between those. And there's a point of inflection there. But again, that is only where you change shape, not direction. Direction, if we're decreasing, we are continuing to decrease, and that's going to be between the points negative 1.1 and positive 1.1. Okay, we are going to go straight into your homework, and I am working out all of the homework problems for you to check your work or see if you can figure out what you might have missed. And again, on the first ones of these, we are looking to identify the x and y intercepts, and you're just reading that from the graph. So hopefully that's not too bad. For the first ones, it looks like your x-intercept is at 0, 0, and it looks like your y-intercept is also at 0, 0. Our next one, our x-intercepts is going to be at negative 2, 0, and it looks like it's at positive 2, 0. And then your y-intercept, you should have at most 1. That's at 0, negative 4. Okay, moving on. This looks like our square root function, number 3. And this is going to be, let's see, somewhere in here. So we have negative 3, 0. And then our y-intercept up here at 0, 1. And moving on to our other functions. This one looks like it's a quadratic. Here we don't have any x-intercepts. We're not crossing the x-axis. And it looks like we cross the y down here at 0, negative 5. Our next one, we have one x-intercept there at 3, 0. And we don't have any y-intercepts there. And then our last one, it looks like we should have a couple of x-intercepts out here and then over here. So we have negative 6, 0, and we have negative 2, 0. And our y-intercept's sitting right there, and that is at 0, 1. Okay, and this is going to follow right along with our notes. The next set, we are looking for our zeros and our y-intercept. And so for the first part, remember we let f of x equals 0. That's going to find our zeros. And so we take the absolute value of 2x minus 5 minus 1 is equal to 0. You always try to isolate your absolute value. And now you set up your two cases. You have 2x minus 5 is 1, and then you have 2x minus 5 is negative 1. Solving this equation over here, you should end up with x being 3, and on this other one, x should be 2. Now let's go through and find our our y-intercept. So we're going to let x be 0. In other words, we're finding f at 0. So that's going to be the absolute value of 2 times 0 minus 5 minus 1. And so we have the absolute value of negative 5 minus 1. So it looks like this one is going to be 4. So we have our zeros, which is going to be 2 and 3. And our y-intercept is going to be 0, 4. All right, so now for our next one, again, same step, same pattern. You will let your function equal 0. And so we're going to have 0 equals x cubed minus 10x squared plus 24x. And again, we do have a GCF here. And that's going to give us x squared minus 10x plus 24. And again, that is our just regular old factoring. It looks like we're going to use negative 4 and negative 6. And then setting each part equal to 0, x is going to be 0. It's going to be positive 6 and positive 4. So there's our zeros for the function. We have 0, 4, and 6. Now for our y-intercept, earlier, I don't know if you recall, we were talking about if every term's got an x in it, then when I plug in a 0, then that's going to generate a 0 because all of that's going to go out to 0 there. All right, our next problem. Again, we have our same steps. We are going to let our function be 0. And so we have 4x to the 4th minus 17x squared plus 4. And this one doesn't have a GCF, so we're going to go through and do some factoring. And looks like we'll do 4x and x because our signs are the same. I'm going to put a 4 here and 1, and they're both going to be minus. Oh, and I forgot something, y'all. This is x to the 4th, so I need x squared and x squared. And then this looks like it'll factor again, since it is the difference of two squares. That's going to be 2x minus 1, 2x plus 1 from this part. And then our other part is x minus 2 and x plus 2. All right, so our zeros from here, we can have 1/2. We're going to have a negative 1/2. We're going to have 2 and negative 2. Now for our y-intercept, we didn't have a GCF of x this time, so we're going to have to substitute in our 0. And that's going to give me 4 times 0 to the 4th minus 17 times 0 squared plus 4. And so that's going to generate a 4. So here we have 0, 4. I think by now most of y'all are catching on that it's just going to be that last number there because it doesn't have an x in it. Or if you don't want to remember that, you're still welcome to stick with the steps we're doing. Okay, and then our next problem, number 10, again, we're going to go through and we're going to let our function be 0. And we'll multiply both sides by 2 to get rid of that 1/2, and 0 times 2 is still 0. We'll square both sides, and so moving 3 over there's our 0 is 3. And then our y-intercept, we do substitute in a 0 here. And so we're going to get 1/2 times the square root of -3. But right here, we're talking about graphing. This is imaginary. So that's telling me that we will have no y-intercepts. It's going to be none there. Okay, for these next few problems, we are going to classify and give the coordinates for each of the extrema. And so here, this one looks like we're going to have extrema there. And it looks like that is going to be the absolute lowest point. So this is going to be an absolute min. And we can write where that's going to occur at. It looks like it's at -1, -7. Okay, for number 12, again, classifying those important points. It looks like at -3, 5, -3, 5, we're going to have a relative max because that's not the biggest value over the entire domain. It's just over a little bitty interval. And then it looks like here at -1, 1, we have a relative min. Okay, moving on. The next one, we've got our graph here, and we have several different points, it looks like here. Even looks like we've got a point of inflection. So let's see, starting from the left side down here, it looks like at -1.5, maybe -8, we have a relative min. And then at 0, 2, this point right here, that looks like a point of inflection, POI, just because it changed the shape, but it did not change the direction. And then we have up here, it looks like at the point 1.5 and maybe about 4, it's looking like we're going to have a point of our relative max. Okay, so for our next set, it looks like, and I'm going to read this from left to right. Now this point here, looking at our arrows, this is going to be an absolute min because it is the lowest value over the domain. And it looks like it's going to be about -0.5 and then maybe down to -5. Somewhere around in there. And then our next one, we're going to have a relative, if we trace along here, that looks like we have a relative max. And to estimate that point, it looks like we're going to have about 1.1-ish, maybe we'll just say 1, comma. And it looks like all the way up to about 6. And then if we turn again here, looks like we're going to have a relative min. And that relative min looks like it's going to be about 2.5 and maybe a -1 point, I don't know, 2 maybe. All right. Okay, now we're going to talk about our intervals of increasing and decreasing. And do keep in mind that we have to remember that we are tracing the graph from left to right. And if we're doing that, that will help. Notice here for our first one, if we are tracing from left to right, I don't see any intervals of increasing there. So I'm going to say here it is none. But then decreasing is going to be over the entire domain. Intervals of increasing, it looks like here if we trace along again, we are going to be increasing in this area. So if we are increasing from there to there, that's going to be from negative, that looks like a -2 to infinity. And then the decreasing's on the other side, so -infinity to -2. Number 17, again, very similar. It looks like we are going to be increasing and No, just increasing. Look at this one. We are going to increase from left to right here. And then when we pick up on this side, we are still increasing. So it looks like we're increasing everywhere. We need to find, looks like an asymptote here. We've got 1, 2, maybe 3. Well, it kind of crosses 3. So somewhere in that area. So maybe at 2.9. So increasing, we are going to be increasing from negative infinity all the way up to maybe negative 2.9, and then on the other side of that, negative 2.9 to infinity. And we do need to note that break there, so do be careful. As far as decreasing intervals, there's none. Our next problem, it looks like we've got a couple of places here. If we look at our increasing, and we do have a point of inflection, but again, we're still increasing. We're just changed our concavity. We did not change our direction. So from there, it looks like it's about a negative 1.2 to a positive 1.2. And then decreasing is going to be from negative infinity to negative 1.2. And then on the other side of that, 1.2 to infinity. Okay, our next problem looks like for increasing is going to be from negative infinity to about 2.5, decreasing 2.5 to positive infinity. And then our last problem, this one's got all kinds of twists and turns in it. So our increasing, we're going to say from negative infinity to somewhere around in here. So we're going to say about a negative 1.9. And then we'll go to decreasing. So I'm going to go ahead and say from negative 1.9 to 0.5. And then on the other side of that 0.5, you turn and go back up. So that's going to be from 0.5 to infinity.